Hey, what's up? This episode is really detail intense, and so I just wanted to give you a couple of warnings. First, we're going to start with a bunch of exercises to kind of get everyone back on the same page and remove all the rust that's accumulated over the months to let us discuss algebras. So there's a bunch of exercises. I don't expect that anybody will have the ability to sit down and work through all of them all at once. So I'm going to put the exercises and the answers to the exercises up on the website. So I'll link to that in the show notes, and I'll also link to the answers in the show notes as well. Second, the calculation details for the final computation at the end of this video are super intense. There's all these factors of minus signs and factors of 2 and 1/2 and so on. So you need to be really cautious about that as well. So I will also link in the show notes to explicit write-ups. I found errors every time I try to edit them. Hopefully there will be no errors, but it should give you enough information to at least perform the calculations yourself. Anyway, without further ado, let's get on with the show. Welcome to our 39th installment in our little series on Vertex operator algebras. This is an important episode. We'll be verifying that the twisted vertex operators can be used to represent the twisted affine Lie algebra sl2 sigma 1 by explicitly computing the relevant Lie brackets. Since by ending chapter 3, this is something of a watershed episode, we'll present you with a series of exercises to help you review many of the algebraic details that we've encountered so far. The build-up should help you follow the intricate calculations of our final commutator. Okay, one last deep breath. Let's go. You might recall that the Lie algebra for SL2, which is represented by the span of the three physicist sigma matrices sigma 1, sigma 2, and sigma 3, satisfy two algebraic relations. First, the commutator that defines the Lie bracket, and second, the anti-commutator that demonstrates these sigmas form a Clifford algebra. Okay, exercise 1. For the Chevalley basis presented here, verify that the following commutation relations hold. Okay, easy enough. Since each of sigma 1, 2, and 3 can induce an involution on SL2, we have exercise 2. Verify that for the Chevalley basis under the sigma 1 involution, sigma is odd, and sigma plus or minus goes to sigma minus or plus. Okay, now SL2 is a vector space, and as such has an inner product. The inner product we'll use is given by the Killing form, which is essentially the trace of pairwise matrix products. The inner product brings us to exercise 3. Verify the following inner products, including the more involution-friendly elements x plus or minus defined at the top of the board. Remember, the inner products are key to the construction of the affine Lie algebra, to which we now turn. The affine Lie algebra associated to SL2, or to any simple Lie algebra, is given by the tensor product of that algebra with the ring of Laurent polynomials in some formal variable t, and some central extension. This means that generic elements in the algebra can be written as products, for which we'll use the shorthand, say, g of m. Thus, the affine Lie algebra is nothing but the linear span of SL2 elements with associated monomials in T, with, of course, C included. The Lie bracket on this space is then given by the SL2 Lie bracket, and a central term proportional to the inner product, relevant only when the degree of the two terms sum to 0. And this brings us to exercise 4, which essentially asks you to verify these commutation relations. Note that we can append the degree operator d to the SL2 hat to form the so-called extended affine Lie algebra. Now, for practical reasons, it's useful to represent these Lie algebra elements as a formal series, which essentially amounts to a sum over another formal variable, z. Hopefully, there's no confusion between the algebra elements g of m and the formal series g of z, the latter being a sort of generating function for the entire set of monomials of the form g of m. And so we've arrived at exercise 5. Defining the delta function and the degree derivation d, verify the following commutation relations of the affine algebra in terms of formal series. Instead of considering formal Laurent polynomials in T, it is sometimes helpful to switch to the variables T to the 1/2. Now, you might ask, why would you do such a terrible thing? Well, for one, representations of the simple Lie algebra sl2 have weights that are integral units of 1/2. But also, this affords a convenient way to extend the involution of sigma 1. So let's call this extended involution theta, and observe that theta acts on t by sending t to the 1/2 to minus t to the 1/2. It also plays double duty as conjugation by sigma 1 on the elements of sl2. Which brings us to exercise 6. Show that the set of elements in the affine Lie algebra sl2 that happen to be invariant under theta are spanned by the following terms, where once again sigma 1 even and sigma 1 odd elements x plus or minus are defined at the top of the board. With that done, you can try your hand at exercise 7, which asks you to verify commutators for the twisted affine Lie algebra sl2. Because we'll need these detailed calculations on formal series, exercise 8 asks you to verify some simple relationships between delta functions, where delta plus or minus z to the 1/2 is defined exactly as delta of z, but with z replaced by the term plus or minus z to the 1/2, just as you'd expect. Okay, exercise 9 reprises exercise 7 in terms of formal series. And this one is super important to make sure that you're aware of all the technical details that are going to go into the final calculations today. And so, finally, exercise 10 asks you to verify a simple relationship between the operator and the delta function. And the hint for all of these kind of formal series exercises is you'll probably want to expand the formal series out explicitly to get started. Whew, okay, done with all of that. Well done, everybody. If you made it through these exercises, you are well on your way to mastering this material. So now, let's turn to the twisted vertex operator algebra construction of the twisted affine Lie algebra sl2. We're going to prove that the two commutators identically reflect the Lie brackets of said algebra. There are going to be some detailed computations involved, so we'll start with some lemmas of increasing complexity. Lemma 1. Let x and y be formal operators that do not commute, but do commute with the commutator x and y. We claim the following relationship holds. To prove this, recall the Baker-Campbell-Hausdorff formula, which, for the specific case mentioned here, simplifies drastically. The lemma follows from a pair of simple computations after applying this fact to both sides. Okay, right on, lemma 2. Recall z here is the sum of integers plus 1/2. Then the formal Laurent series here is given by minus some particular logarithm. To prove this, simply expand the logarithm of the ratio into a difference of logarithms, then apply the formal series definition of a logarithm as a series. Combine these two series together and observe that half of the terms cancel. What's left over gives us the result. Okay. Lemma 3 is again some relationship we'll need in the computation that follows today. To prove that, simply expand the denominator in a series, then include the numerator as appropriate. Pull out the 0th term in the sum and combine the other two series. And now we square it and expand, and we find 3 terms, including one double series. Resum that double series by considering fixed values of m plus n. Since m and n have a minimum value of 1, there are m minus 1 such terms for each fixed value of L, which combine to give us our result. Now, remember those crazy operators E that we defined earlier when discussing twisted vertex operators? Lemma 4 amounts to a formal question about the relationship between their ordering. If you're worried about summability and the well-defined nature of this product, hey, well, good on you. We're going to be using this result inside a bigger product of other operators, which will be manifestly well-defined. So don't worry about that right now. Now, to prove lemma 4, let's consider the series that form the arguments of the relevant exponentials. Since alpha and beta here are both proportional to sigma in the present case, the only commutator that we need to worry about is proportional to the central term. But by lemma 2, this is just given by the logarithm of some ratio. Pushing the coefficients to the power, as is the style with logarithms, the result follows directly from lemma 1, recalling that c is used as the identity operator. Incidentally, this is one of those instances where it's nice to kind of carry C around to see what goes wrong if we hadn't assigned it to the identity operator, at least upon acting on our Heisenberg submodule. There is a near immediate corollary to lemma 4, namely that the normally ordered product of twisted vertex operators X can be related to their simple product in terms of that by now familiar ratio of formal variables. So to prove that, recall that X is defined in terms of the E operators, which give us the normally ordered product that explicitly rearranges E minus, E minus, E plus, E plus. Remember, all minus signs go to the left, all plus signs go to the right, as per the definition of normal ordering. Notice that the distinction between the normally ordered products of X's and the kind of regular product of X's amounts to the order of the middle two operators here. So an application of lemma 4 verifies the corollary. Finally, armed with all these results, let us return to prove the proposition. Okay, we have two commutation relations to verify, and the first one is relatively simple. Recall that from lectures 36 and 37, the twisted vertex operator X is the unique solution up to an overall scalar of this system of equations. So for H identified with sigma and alpha as either plus or minus sigma, the first result follows practically by design. Thus, we are left to compute the commutator of the two twisted vertex operators, which is the meat of the episode. So let us begin. Recall the corollary we just proved relates the product of two copies of X to their normally ordered product. Now, this huge mess will simplify, as we'll now see. So thanks to the exercises in the first part, you know that the inner product of sigma with minus sigma works out to minus 2. That, together with lemma 3, allows us to rewrite the commutator as a difference of series. Note that the different terms of simply 1 kind of cancel out in this difference. We can combine these two series into a single sum over the integers, as the 0th term is trivial. See, much better. Now, recall the twisted vertex operator can be written in terms of the inverse of the degree derivation. So plugging these values into the computation of the commutator, we find. Now, this series can be re-expressed in terms of the delta function to give us a somewhat simpler looking expression. But as we'll see, this is going to be one big tedious mess to compute. Or at least it would be a tedious mess if we hadn't already done the computation in lecture 29, where we discussed the derivation of formal series. That result, you might recall, involves some formal series times d delta of a ratio of variables. Comparing with the commutator we've been computing, we can apply the result that we studied back in chapter 2 to complete this computation. So the result in question is presented here as a sum of two terms, but unfortunately it requires integral powers of the formal variables, which is only slightly annoying because we've been dealing with half integral powers of z and w. So to that end, we simply redefine our variables to x and y. This redefinition extends to our results as, which requires some careful bookkeeping of various factors of 2 from the chain rule, and the degree derivations big D. Now, if we identify the normally ordered product with that formal series z of x and y, we find that, for example, z of x and x is equal to 1. Moreover, the derivation of z just kind of pulls down a factor of 2 sigma. So again, identifying y with x, we find a similarly simple result. So, putting all these results together, we find a pair of terms that hopefully looks sort of familiar. Now, replacing x and y in terms of our original variables z and w, we find the final result, which verifies that yes, the commutator of twisted vertex operators reproduces the Lie bracket of the twisted Lie algebra sl2 of sigma 1. And so we're done. Okay, so where are we? Well, we've just shown that the twisted vertex operators X, acting on the Heisenberg module V, extend the module to an irreducible representation of the twisted affine Lie algebra sl2. Actually, they provide us with two distinct irreducible representations, where the roots sigma plus or minus are identified with either x of plus or minus sigma and z, or minus x of plus or minus sigma and z. And that's our show. And we're also done with chapter 3. So good job, everybody. Next time, we'll start to dig into the untwisted case. See you soon.